Please welcome from Heptio, Ross Kukulinski, and from CoreOS, Luis Pabon.
Good afternoon. How's everybody doing?
Yeah, it's the last one, no?
So, my name is Ross Kukulinski. I just recently joined a new startup called Heptio, founded by two of the three people that created Kubernetes. I've been active with Kubernetes for almost 2 years now. Also active in the RethinkDB community. I have an introduction to CoreOS video course from O'Reilly, and you can find me on Twitter @Ross Kukulinski, and also on GitHub.
My name is Luis Pabon, and I am the technical lead of the Kubernetes development team at CoreOS. And before that, I joined CoreOS about 6 months ago. And before that, I worked at Red Hat Storage for about 3 years.
Excellent. So I'm going to sort of introduce things, and then we've got some demos from Luis. So I love it when the keynote, the first keynote, Alex is sort of saying, why do we have this myth that you can't run storage systems on Kubernetes? Thou shalt not run a database on Kubernetes. False. Thou shalt take care running a database on Kubernetes. And that's really what we're going to be talking about today. So before transitioning into the world of containers in about 2013, I was happily managing deployments of MongoDB and Redis using a configuration management tool called Ansible. Since that time, however, I've had the opportunity to work with a number of companies with a bunch of different business and technology needs. And to that end, I've deployed and managed each of these stateful systems in Kubernetes for production workloads. And for many of them, Kubernetes has enabled me to manage larger database clusters and more of them with less work than I could with Ansible. And a lot of that has to do with the declarative approach that Kubernetes takes. As a developer or an operator, I define the state of the system that I want, and then Kubernetes will make the necessary changes to get the system into that state. And so in this example, I have an application called My App. I have 3 instances of it running, and I've got my container image. So if I wanted to update the container image to a new version, all I have to do is make the change to My App 1.0.0 to 2.0. Kubernetes, the API, and the scheduler, and the controllers will automatically make the update to make sure that the system is now running that. Now, it's one thing for a developer to Dockerize their application and ship it to Kubernetes. It's actually relatively straightforward, which is great. But data is a persistent problem. It's a whole other problem and skill set to operate and manage databases and persistent storage systems. How does your database scale? How do you do backups? Perhaps more importantly, how do you do restores? Do you test your stores? Where do you put your data? Are you in a cloud provider or bare metal? Where does your raw bits go? And that's really what we're going to dig into today. So to kick things off, I'll share how Kubernetes abstractions allows us to manage stateful applications at scale using RethinkDB as an example. Next, Luis will demonstrate stateful sets hands-on. And then finally, we'll come back and talk about the future of persistence and how Kubernetes is going to enable that moving forward. Now, since we're talking about persistent storage and databases, I think it's best to have an example. And in my case, I'm going to use RethinkDB as an example. So some background. RethinkDB is a cloud-native database. It's now owned by the Linux Foundation. The corporate company has shut down, but the CNCF purchased the rights and the IP rights for RethinkDB and donated them to the Linux Foundation. And I've been involved with that process sort of behind the scenes. Now, RethinkDB as a cloud-native database, it's a similar class to Elasticsearch, CockroachDB, or Cassandra. These databases are all built from the ground up with failure in mind, making them ideal for running on Kubernetes and in the cloud. So that's one reason I wanted to use RethinkDB as an example. The second reason is I've been running RethinkDB on production since March of 2016. That was all the way back on Kubernetes 1.1, a long time ago. And a lot of companies actually picked up and started using my manifests as a way to get started running Kubernetes, and they ended up sort of owning that lifecycle themselves. Now, over the last year and a half, a lot has changed in Kubernetes features, and I'd like to share how managing stateful services like RethinkDB worked in the past and how it works now. But before we do that, let's look at what a cloud-native database might need from its infrastructure. So number one, process management. We need something that will start our RethinkDB process. We need something that will restart it if it crashes. And we need something to schedule it if we're in a distributed system like Kubernetes. Where does it go in terms of the infrastructure? Consistent naming. So a lot of databases that have a built-in clustering mechanism require a unique name, and they expect that the node, the process that has some data, always comes up with the same name, no matter where it is. Persistent storage. We don't want to lose our bits just because our pod moves somewhere else. So if we're running in a cloud provider or running on bare metal, we need some way to keep those bits safe, no matter where our pod or application happens to be scheduled. And finally, pure discovery. If we have a cloud database that has a built-in native clustering, those pods need a way to find each other so that they can build that quorum mechanism, whatever they may have implemented. Okay, so Kubernetes 1.1 was originally released in November of 2015. So for process management, back then, we had this thing called a replication controller. It's still around, you can still use it. So what we had to do is we define one replication controller for each RethinkDB sort of storage node, a replica that we wanted to use. And the replication controller managed the lifecycle of that process. So it would start at that instance, it would be scheduled somewhere in the system. If that process died, the replication controller sort of managed the lifecycle, would restart it and reschedule it as necessary. Consistent naming. So still in the same file, we had to hard code the name of this instance. Here, the instance name is replica 1. And so for every replica that we wanted to have, we had to have a different replication controller to file defined that had the statically named files. Now, this makes updating and reconfiguring RethinkDB a very manual process. If you have a 50-node RethinkDB cluster, if you want to update your version, you have to update 50 different files. Okay, let's talk about persistent storage. So Kubernetes, pretty much as long as I can remember, has had the ability to connect to network-attached storage, whether that's your cloud provider, like Amazon with Elastic Block Storage, or Google's persistent disks. But before I can even create this replication controller referencing this disk called RethinkDB-storage.1, that PD name, I have to go to my cloud provider, create the disk, and then I can reference it. If I don't have that disk created for me, this replication controller will start, but the pod will be pending. It's waiting for that disk to exist. So this is another manual step that I have to do whenever I'm managing this lifecycle. Okay, pure discovery, the fourth component. So the way we used to enabled our RethinkDB instances to connect to each other, we actually had a small bash script that ran before we started the RethinkDB process. We called it run.sh, and we used the Kubernetes API. So every RethinkDB pod had access to the RethinkDB API, could query and find the list of endpoints that were defined by the service. This is how they found each other. Now, I view this as bad security practice. There's no reason my RethinkDB nodes need to have access to the Kubernetes API, especially at the time when we didn't have role-based access control. So essentially, my RethinkDB nodes had complete access to manage my entire Kubernetes system, whether I liked it or not. Now, there was another mechanism that you could have done to manage this service discovery, and there's some folks that had done some early MongoDB work, and they defined a Kubernetes service for every replication controller. So replica 1 would have a service 1. Replica 2 had its own service 2. And that service then gave a guaranteed DNS name and IP address that were consistent. Still a very messy manual process. Okay, let's jump forward to Kubernetes 1.3, July 2016. So we have this new thing called deployments. This definitely made our life easier. So deployments shifted the complexity in the lifecycle management. If we want to make an update, replication controllers, all of the updating of pods were all done from the client perspective. Client meaning kube control. So if you wanted to update something, kube control was responsible for making all those changes and running that control loop. Deployment shifted that complexity to the scheduler and to the master API server. So this made things easier in terms of the lifecycle management of updating. But we still have to copy and paste this deployment file for every new version of our replicas that we want. Persistent storage. So we had a new thing that was added, persistent volumes and persistent volume claims. These enabled us to have a small break in abstraction between the replica that I'm defining as an operator, as a user of the database, and the infrastructure piece of actually creating the disk. So somebody else, some cluster administrator, could create a bunch of persistent disks. They could log into Google Cloud or Amazon, create 10 disks, give them unique names, and assign them to persistent volumes. And then as the RethinkDB operator, I can sort of claim them with the PVCs. But still, someone has to go in and create all those disks. There must be a better way to do that. Okay, Kubernetes 1.4, so now we're getting close. This is September of last year. Persistent storage had another big leap in capability. Dynamic provisioning was now a system that was built into Kubernetes by default. What dynamic provisioning allows us to do is define a storage class. A storage class is something that enables us to specify a certain provisioning agent. So there's provisioning agents for most of the major cloud providers. And I can define different parameters. In this case, PD-SSD means a Google persistent disk that's of type SSD. I can also make settings like which zone or availability zone my disks are in. And this then enables me in my deployment to be able to make a request via persistent volume claim. And Kubernetes will automatically provision the disk for me, connect it to the right node that my pod is running on, and then make it link up into my pod. So now this is dynamic. This is great. I don't have to worry. I don't have to log in my cloud provider anymore to get new persistent storage for my applications. Kubernetes 1.5, December 2016. So this is new. Stateful sets. They used to be called pet sets. They were renamed as they moved to the V1 beta. And stateful sets were really created to tackle some of these hard problems that we were experiencing in managing databases. So stateful sets are really valuable for any applications that require one or more of these sort of capabilities. So in terms of consistent naming in our world, now when I define a RethinkDB stateful set, every instance, as I scale up or scale down, all of the names are always named the same. RethinkDB-1, 2, 3 to 500. And if I scale back down, the highest number ones are removed. So there's always a consistent naming scheme throughout. Persistent storage is also nicer now. So now instead of having to define a persistent volume claim for every deployment, we define a template. And the stateful set will manage and create persistent volume claims for every instance of our stateful set. And then we have the dynamic provisioner that's running that will create our persistent disk in our cloud providers for us. Now we're getting there. Now we're sort of almost all automated. Peer discovery. So now I don't have to do my hacky way of using the Kubernetes API. So the Kubernetes stateful set leverages a headless service. So basically there's a service that's defined. It doesn't have a cluster IP address. But every instance in the stateful set, its IP address and its port are part of the StatefulSets SRV records, meaning you can do a DNS query on that name, so my RethinkDB cluster.pod namespace, grab the first value of all of them. That's my list of other RethinkDB instances that I can now join and build my cluster around. So that's a quick high-level overview of stateful sets. I want to invite Luis back up to do a live demonstration of what stateful sets look like.
Thank you, Russ. Okay, so also a lot of cool information. Let's go ahead and take a look at a demo of running stateful sets on AWS. So what we have here is first, we're just going to show the nodes are available on AWS. And then some of them are master nodes, some of them are just regular nodes. And what we're going to show here now is a very important part is what's called the storage class, which defines how is it that volumes are going to get automatically created by the dynamic provisioning. So as you can see here, let me just pause that right there. We have some parameters that we're going to give to the system, to the dynamic provisioner. And we're just saying to the dynamic provisioner EBS to create these as GP2 volumes. We could also define more information right there, like IOPS and things like that, if we want to be more specific on what type of volumes to create using this specific storage class. But for the simplicity of the volume, the demo, we're just going to keep it as simple as possible, just use the normal GP2. So now what we're going to do is look at this YAML description of a CockroachDB database. The first thing we're going to have on the top is a service to be able to access it. But the second thing is very important is a service, what's called a headless service, so that the stateful set pods are able to find each other. And the really key thing to have here is that part there is called cluster IP none. Once you set that, it defines that the service is a headless service, and that makes it simple for the pods to be able to find each other in a stateful set. The last thing we need to do is to verify that the storage class has been set. This is how Kubernetes is told, or we ask it to create new storage system devices to be able to attach to each one of the pods in the stateful set. All right, let's take a look now at what happens. So now what we're going to do is we're going to go ahead and submit that to Kubernetes. And it goes ahead and we have the services and we have the stateful set in there. So we're going to take a look at the pods. And as you can see, the CoreOS-DB-0 is the first one to start. And then so on, CoreOS-DB-1, and then 2. So we're only asking for 3 in this demo. There's also a very simple way that we're going to do to be able to scale up or scale down the stateful sets. We can add more as needed. So let's take a look now at the pods running. And now we're going to take a look at looking at the actually increasing the stateful sets by 1. And this is as simple as just increasing using the scale command from kubectl and increasing the number of replicas. We could have put in 100 of them right there, and they would have all found each other. But we just added one more for the simplicity of the demo. And it has connected, and it's running now. So that is the power of the stateful set. Not only that, but each one of these, as soon as it comes up, is assigned a brand new disk from EBS according to a storage class. So what we're going to do in this part here is to make sure that the stateful sets can see each other. We're going to show how is it that we can reference from one pod to the other using DNS. Now, one of the things that I didn't know was while I was doing this is I kept referencing the pods by the pod name. So that doesn't work. You have to use the pod name dot the service name, and that's how the DNS service actually works, and you'll be able to find each other. So, which took me a while to find out, trust me. So now that shows that each one of the pods has a different IP address. You can see that we got CoreOS-DB-0 has an address of 2312, then the other ones have 229, and so on. So now let's take a look at the persistent volume claims. Each one of these has been automatically provisioned for each one of the pods in that stateful set. It's really nice because you can, if you wanted to get more, like say if you wanted to bring it up to 50 pods, all we have to do is scale it up to that much, and Kubernetes automatically assigns those disks to it. The really nice thing too, but there's a caveat with that. So when you bring down the stateful set down to, for example, replicas of 0, you want to upgrade them. So to upgrade them, you have to change the image value, and then each one has to reboot or restart the container. You don't want your persistent volumes to be deleted. That would be bad. So then your entire database will be gone if you do an upgrade. So instead, what happens is, even as you can see here, I deleted the stateful set CoreOS-DB, but the persistent volumes are still there. So it is your responsibility to be able to delete those. So we're going to go ahead and delete those now. And it's just as simple as looking at the persistent volume claim, pointing at it, and deleting it. I was really lazy there, so I just do arrow up. I could have done a for loop, I'm sure, but that's good enough. So let's take a look now. Continuation. All right. So we showed how stateful sets work on the cloud. Very nicely, well set up with EBS. What about on-premise? What if you have bare metal setup or just VMs or some other model? Well, let's take a look at the traditional storage model. And I mean traditional because this is the way we've been using storage and compute for the last 30, 40 years or so. And here what we always talk about is compute on one side and storage on the other. It's how we deal with, like, if you set up OpenStack yourself, you always have compute of Nova, for example, on one side, and it's connected to some type of storage system that's separate from OpenStack. So we have, way back, we had mainframe, and then we had open systems, And then we had virtual machines. That was around the 90s to 2000. And then you can still do it today with Kubernetes, right? So Kubernetes today on bare metal can attach to a storage system, just like OpenStack, just like anything else. But wait a second. But Kubernetes is something different, right? Couldn't we containerize the storage system, the storage software, and been able to deploy it onto Kubernetes? So let's take a look at a brand new architecture. Well, we think of Kubernetes as the data center operating system, right? So what we say now is that we don't only have to have one storage system, we can have many storage systems, all managed by Kubernetes. Because a storage system, in essence, is just a process, right, that runs on some compute that is taking over some disks and provides that storage back to Kubernetes. So this model here, what it defines is that now, as an administrator, I can use all my Kubernetes APIs, all my models, deployment and such, to be able to manage thousands of machines, not just my applications, but my storage applications also. So we're going to take a look. And then we have some companies that are going through and actually doing this. So for example, we have GlusterFS, which is an open source distributed file system, and we have Rook, which is based on Ceph. And these two projects, what they're doing is they're containerizing their storage software and being able to then deploy it on top of Kubernetes, being managed by Kubernetes. And then we got these other two companies, Portworx and StorageOS, which have containerized their storage software, and they're on the way to being able to be managed by Kubernetes itself. So let's take a look at a small demo here. So in this demo, what we have here is we have 3 nodes. Each of these nodes has one 100 gig disk. It's actually VMs on my laptop. And as you can see here, we have GlusterFS running as a deployment with Heketi as his volume manager. Okay, it's how you dynamically create volumes in GlusterFS. So all this entire cluster of storage is running on top of Kubernetes, and it's being managed by Kubernetes the way it manages any type of deployment. So if any of those nodes die, or the GlusterFS pod dies, it gets restarted automatically by Kubernetes. So we have here also is a storage class. Now the previous one I showed you had the EBS, it pointed to EBS volumes. This one instead points to using GlusterFS dynamic provisioning. Now, all we need to do is go back to the CoreOS. Instead of using the previous one with AWS, we change it to the new storage class to use GlusterFS. And then we go ahead and deploy it. We didn't change anything else in CoreOS. All we said was, now get storage from that storage class. So now we look at the pods and we see that CoreOS is now starting to come up. And now we can also see that it has a persistent volume claim provided by GlusterFS, who's also running on Kubernetes. Now we can see here that CoreOS is starting up. We have a few more of these Stateful Sets pods coming up. But it's a really nice, interesting system going on here, where the one operating system, Kubernetes, can manage both the storage system, or many storage systems, and the application. So now CoreOS is coming up. We're going to skip a little bit further. Now it's fully come up. So what we're going to do now is that just to check, we're going to use Kubernetes exec to go into one of the GlusterFS pods and look at some of the values in the disk to check if the CoreOS had written data through the GlusterFS volume. So we're looking way in there inside GlusterFS, and here is the data from the database. We can even look at the CoreOS version. So that's pretty cool. You saw that works very well for on-premise. Now you can take your systems with just disks and stuff in them. You don't have to buy expensive storage systems. You can just deploy, just include storage systems with disks on them onto your Kubernetes cluster and deploy onto that storage containers. Be able to manage that all through the Kubernetes API and then provide that storage back to your system. Sometimes we have nodes with 1 or 3 disks or 4 disks, and those disks have not been utilized. But now you can utilize those disks by using a storage container. So that was great for on-premise. Let's take a look at this now in AWS. So we had the same 3 nodes and 6 nodes as before, but now we have each of the 6 nodes has 3 256 gigabyte EBS volumes attached. And then what I did was, let me go back to this model now, is I created a namespace called storage in pods. And we refresh the page, probably, no, there we go. And you can see here, I have GlusterFS running on AWS. So now, what we're going to do is live demo, yay, right? Everything's gonna break, just wait. So now what we're gonna do is we're gonna do it by hand, and we're gonna change the values. So let's say kubectl, get nodes, make sure we're communicating. Okay, we're good. Kubectl. And again, if you have any questions, you can go ahead and ask, and I can see if I can answer or check anything you want me to check. Kubectl, let's see, get storage class. So here we have the storage classes for both EBS and GlusterFS. Ours is called GlusterFS QM storage, so let's go ahead and change that. Cockroach. Gluster. Is it GlusterFS or Gluster? I forget. Gluster. Ah, darn it. All right, so now we say kubectl get pods. This is the default namespace. There's nothing in there. So I'll create Jeff. Yay. All right, so let's go back to the UI. Let's go to the namespace default, and there it comes. Nice. It's not ready yet. It's running. So now these volumes, instead of using EBS, they're now using GlusterFS on the cloud. So now let's do kubectl get PVs. No, PV. There we go. So why would you want to run GlusterFS in the cloud? Don't you have already EBS volumes? Why would I want to do that? Well, there's a couple of things that you want to avoid. So one of the things that it provides for you is that GlusterFS can do things like geo-replication. Think of it this way. What if you have a database here and a database in another cloud, another vendor, or another region? There's features sometimes from container storage that you may require for your application to run. You also avoid the issue, and we can go to more about this later, but of availability zones. So for example, if you have a node that's in one zone and the container runs on there from the stateful set, it will get an EBS disk on that zone. But if that node goes down and there's no more nodes on that availability zone, even though you have other zones with plenty of space, that container will be pending forever until one is available. Now with GlusterFS, you will not have that issue because it'll just go to another node and reattach to GlusterFS cluster and its volume. All right, any questions on this before I continue? All right, you guys are just mind blown, right? Oh my goodness. So, all right. Let me give it back to Ross now. Thank you.
Thank you, Luis. Give him a round of applause. I'm always normally very nervous about doing live demos, so yeah, it went well. Okay, so let's talk about the future of persistence. So operating databases is hard, and so things like stateful sets help, with that process. But these are really just fundamental building blocks for us to build on. And if you've managed stateful applications like databases and storage systems, it's a challenge, especially as you increase scale. And these systems really do require human operational knowledge to correctly scale, upgrade, reconfigure, handle downtime, while at the same time making sure you're not losing any data. And so Kubernetes provides primitives, like stateful set, things like jobs, that make it easier to manage those lifecycle. But at the end of the day, right now, you still need to have a human that's managing that. So the RethinkDB work that I was doing back in 1.1, 1.2, sort of the crawl stage. You could do it, but it was hard. Dealing with backups and restores were non-existent, I'll be perfectly honest. Now with stateful sets, we're sort of in that walk phase, right? So you actually can run stateful systems pretty well, but there's still more. We need more. What's going to take for us to be able to run to really accelerate how we manage and build and deploy complex stateful applications? And I think the answer is the operator. So the operator paradigm was something that CoreOS introduced in November of 2016. And the basic idea is taking all of the human knowledge that we have at managing these complex systems and put them in code. Put that code into a container, run it inside of Kubernetes, and allow it to manage those stateful applications for us. And the operator workflow really is just another Kubernetes controller loop. So you define the state that you want. So if you've been to any other talks, I think there was a talk on etcd and Prometheus operators. You define the state you want. I want an etcd version 2, and I want 3 replicas, and I want it to have this amount of storage space. And your operator will observe the current system, analyze it, and compare it to the state that you've requested, and then it will act. It will make changes to the Kubernetes system to get it to the state where you want. And it's important to note that these operators have 2 really important aspects to their knowledge. Not only do they need to understand how to interact with Kubernetes, so they have to be able to talk to the Kubernetes API and understand those things, but more importantly, they need to understand your application or your database. So in the case of the etcd operator has to understand the size of the cluster and be able to communicate with the etcd API to make intelligent decisions about scaling up or scaling down. And these operators are also doing more advanced things, like backups and restores and lifecycle management. So when CoreOS first announced the operator paradigm, they released alpha versions of the Prometheus and etcd operators. And already, just in the last 6 months or so, we've seen an explosion of operators. There's Postgres operator, there's Elasticsearch, the Rook folks that are managing storage systems, and Quartermaster, which was what Luis used to deploy a cluster. Those are all operators. You deploy an operator, you define the state that you want. I would like a cluster with this amount of storage space, and the operator will make the changes necessary to do that. Now, it is important to note that all of these operators are either in alpha or recently promoted to sort of beta state. But we're going to see more and more companies rally around these projects to really simplify the deployment and management of these stateful systems. And Luis and I, both really think that 2018 is going to be the year of state on Kubernetes. We think these technologies like operators are going to have a massive impact on how businesses deploy and manage stateful systems and complex applications on top of Kubernetes and in the cloud. And if you're considering running a database or storage system on top of Kubernetes, I highly recommend doing a quick Google, look to see if there are any operators that are currently in development, rally around them, or if there is none, create one yourself, open source it, make it available. One of the things that I really enjoy working in the Kubernetes community is that it's a community. We're all helping and working together to make it easier to build and ship product. At the end of the day, that's what we do this stuff. We want to build products, we make our business more valuable, and we want to do it faster and more efficiently. That's what Kubernetes allows us to do. And as a platform, it's extensible. We can build more complex things on top of it. And with that, thank you. And I see we've got time for questions, so please raise your hand, and the gentleman with the microphones will find you. Oh, come on, just because it's the last talk doesn't mean you don't have questions. There's one in the back there.
They're just in shock. I think that's what it is.
Yeah, so I'm wondering if anyone is doing any type of chaos testing on the reliability of the data in these systems.
That's a great question. I don't know of any. I mean, I know the databases themselves are, most of the cloud native databases go through the FR tests, where they basically check to see how does it handle network partitions and downtime and those types of things. I don't know if anyone who's taken and applied that when running them inside of Kubernetes with an operator-based paradigm.
Yeah, I don't think so. I haven't heard any.
Does anybody in the audience know of anything that's doing that? Okay, so apparently the etcd operator is doing that. So it's probably part of their release cycle. Good question. Other questions?
On the persistent storage, you mentioned about GloucesterFS, a couple of other. Have you also certified or tested with NetApp, EMC in the cluster mode?
So those systems, again, are they in the traditional model?
Right.
So that's just normal connection
Should work.
from, yeah, absolutely. Okay. Yeah.
I think the question that people mostly have about stateful systems is about trust and being driven by the fear of losing your data. Haven't worked in like database level stuff much, but I imagine that the reaction of a seasoned DBA is going to be total fear of this. That they're gonna think like, oh, cool, some kids can write a Go program and it replaces 30 years of knowledge of what I've done. That just feels like the gut reaction of anyone who does this for a living. Do you think there's anything other than just the time of showing this can actually work that could help to alleviate that fear? Like how do we gain trust that this is a safe way to handle our data?
Yeah, I think this is a good question. I think that first you have to talk about the storage layer, and then you have to talk about the application layer. And at the storage layer, I think you want to make sure that that system is as reliable as possible. So that's why it's hard to take a brand new system that's being created and then being placed on as container. But containerizing an existing very reliable storage system is definitely a very good way to be able to put that in Kubernetes. Now, remember that running in Kubernetes it's just a process management, right? It's not stopping anything. It's not inducing any I/O issues, it's other than just the networking part. So from the storage layer point of view, GloucesterFS running to disks, there's no issue there. Now, if it has to do with the issues of restarting and things like that, that's where Kubernetes comes in and it's a little new. But I would say that that's very reliable at the moment. The next part then is to talk about the application. And again, you take an application that's brand new, or you take an application that's very well tested and then containerize that. So if you take a very well tested application, then your trust level is better because you're just saying that the application is just running in a controlled manner, right, by the runtime. So once the I/O moves through the application to the storage system to the disk, that brings more trust. Now, again, if I was, like you're completely correct, if I took a brand new storage system with a brand new application on top of it, that would make me nervous. But taking a system that's been around for more than 10 years, taking an application model that has been around for a long time, very well tested, then that's okay.
One thing I want to add, so I did a variation of this talk at a database conference 2 or 3 weeks ago, and I had some really awesome conversations afterwards. And the thing that I sort of realized in having those conversations is that a lot of these people were using tools like Ansible or Puppet or Chef. Configuration management, you define the state. Some of them you define the state, and then they make sequential actions, and if it blows up, then an operator gets paged and have to go validate that. And in some ways, the operator paradigm is the next generation of managing that. Right? So instead of writing a bash script that does lifecycle management and backup and restore, I'm writing some code that it's easier to test and validate. Right? So I can write unit tests for Go and validate and mock out the database interactions themselves. And so I sort of view that as the next generation and makes it easier to manage those more complex systems at even larger scale. I think there was another question over here. Yep.
Right here.
Oh, go ahead.
When the CockroachDB instances were coming up, it seemed like they were coming up sequentially. Is there a reason they're not done concurrently, and can it be done?
The reason is that's why the stateful sets were implemented. They were done on purpose sequentially, which I would say if you're doing 100 of them, it would take some time to come up. But that's the way that it works right now. The exact reason, I think it's probably for discovery, or be able to come up slow and be able to then to deny provisioning on time and so on.
Yeah, there's sort of two pieces. One is the discovery aspect. So you want to have one up before
Yeah.
you bring up the next one so it can find the one that's already running.
Yeah.
And there are some databases that are really sensitive to the order in which you bring things up, and that's why it was implemented that way.
And also, you'll know that container -0 is always up if you're up. And if you call -0 and you using the hostname, you can find out if you're the first one. So it makes actually peer probing and finding the peers very easily.
I think we've got time for one more.
You mentioned trusting the application and trusting the storage. What about trusting the database? Because I trust Postgres as a database. It's been around for 20 years.
Yeah.
Say I've been using it for 5, 10 years.
Yeah.
So for me, trusting PostgreSQL is different than trusting a different database.
Yeah.
So what about the database there?
Yeah, I mean, you want to take this one?
I mean, I think if you're happy with Postgres, then rock Postgres. If it solves your business needs, I don't see a reason that you have to switch to a different database.
Yeah.
However, I will note that if you look at databases like Postgres and MySQL that fundamentally are built to be on a machine and not ever move and
With
scale
HA.
up instead of scaling out.
Yeah.
If you're running in a cloud environment that's a little bit more dynamic, like Kubernetes, you have to design for failure. And some of these newer generation of databases are built from the ground up to do just that. And so they are able to scale horizontally, and they're more, have built-in mechanisms to fail directly. And I had a very lengthy conversation with one of the people who runs the Postgres US conference, and he's been in the Postgres community for a long time. And we had a lengthy discussion. He's like, yeah, don't run Postgres in Kubernetes. There are things you can build on top of Postgres that make it easier, but direct Postgres doesn't. So those are things to think about. And just because you can run your database in Kubernetes doesn't necessarily mean it's the right solution for you. If you love Postgres and you already have existing infrastructure or teams that manage Postgres at scale on VMs, just keep doing that.
Yeah.
In Kubernetes, you can always reference external services.
Yep.
Your developers don't need to know that the database is in or external to the cluster. That's part of the beauty of the abstractions in Kubernetes. Okay, I think that's it. Thank you very much.